So before we graphically derive the expression for overall mass transfer coefficient in terms of individual mass transfer coefficients, let's try to visualize, what situations we have here. So we have, say as an example, absorption column. So we have an interface of gas and liquid, and say sulfur dioxide in air diffuses into water. Okay, so we have two individual resistances, one in the gas film and one in the liquid film. So when we say there is a resistance in the gas film, there is a concentration drop. So we have the bulk concentration Cb, and it drops to some interfacial concentrations, and at the interface we have the equilibrium between the gas and the liquid phase, and then there is a concentration drop within the liquid phase before it levels to some bulk concentration in the liquid phase. So we have four concentrations, okay, two at the interface in equilibrium and two bulk concentration in two different phases. We can also have, as we said, C star or Y star and X star, assuming the entire bulk concentration in the liquid phase is at the interface, or assuming we have the entire gas phase bulk concentration or vapor phase concentration at the interface. Okay, so with that, let's try to obtain this relation between the overall mass transfer coefficient in terms of individual mass transfer coefficient. So we have the interface, gas and the liquid, two individual film mass transfer here. So we have the bulk concentrations, say in the gas phase, mole fractions YB. Okay, so we can say YB here, and then it drops to the interface, say YI, then it drops from XI, where YI and XI are in equilibrium, this concentrations, to this bulk phase at XB. Gas phase we have some Reynolds number, in the liquid phase we have some Reynolds number based on the flow rates. So this Reynolds number decides what is the individual mass transfer coefficient in the gas phase and in the liquid phase, okay, based on Reg and Rel. And we have this diffusion flux across this interface at Na moles per second per meter square. We also said that for YAB, corresponding to YB, there will be XB star. Okay, we can have X star here, and corresponding to this XB, we can have Y star here. Okay, so these are the different concentration levels which we have marked here, and then corresponding to this, if we draw this line Y versus X mole fractions, then we have this equilibrium curve, say solubility data, Y is a function of Fx. We mark this bulk concentration, so we have X, say let's say YB, and we have XB. Now we know from the slope of minus Kx and Ky, Kx to Ky, we can draw this line here to obtain Yi, and we have Xi. Okay, all right, so we can draw these, we can complete this geometry here like this, and we have like this. If you recall, this is your M dash, this triangle, the slope, and this slope here is M double prime. Okay, so let's look at this. We have YB here, YI here, okay, and we have XI, and we have XB coordinates here. So we can write equivalent to this X, equivalent to this XB. We can also have, as we said earlier, Y star, and equivalent to this YB, we can have X star. Okay, so XB, XI, X star, and we have YB, YI, Y star. So go back to the previous YB, YI, XI, we have XB, and equivalent to this YB we have X star in equilibrium with YB, and in equivalent to this XB equilibrium with XB we have this Y star. So these points if we mark, and now we focus on this YB minus Y star, we can write as YB minus YI plus YI minus Y star. Okay, so let's go to the next. So we can write here YB minus Y star equal, this equals YB minus YI interfacial concentrations plus YI minus Y star, and this YI minus Y star now we can write as M dash M prime in terms of now liquid phase concentration, which is Xi minus Xb. Okay, now we have the definition for diffusion flux in terms of concentration drop and mass transfer coefficients. So we have now Na over capital Ky. So this is overall mass transfer coefficients, defined as Na equals Yb minus Y star into Ky. So recall the previous lecture we had. Similarly, we can write Yb minus Yi as Na over small Ky. So individual film mass transfer coefficients plus M dash Xi minus Xb we can again write as Na over small kx film mass transfer coefficient in the liquid phase. So we obtain the same relations which we had earlier. Ky equals 1 over small ky plus M dash over kx, where M dash is the slope of the solubility curve. So this is the slope of the equilibrium curve or the solubility curve in this compound, in the present case equilibrium curve. Similarly, we can write how one should obtain. You can obtain as an exercise 1 over kx as 1 over small kx plus 1 over M dash double dash over ky. Okay, so we have obtained the similar relations which we obtained earlier. Overall mass transfer coefficients in terms of individual mass transfer, Ky, Kx based on the gas phase or based on this liquid phase. Okay, now let's try to understand that what we have here. So we said that we have an interface and two diffusion films, right? Two films, one in the gas phase, one in the liquid phase. So these are the diffusional resistances. Okay, just like you have an electrical circuit and you apply a voltage drop across a wire, and you have two resistances in series, R1 and R2. So the voltage will drop from say VA to VI intermediate and VI to say VC or VB. So entire VA minus VB is distributed over two individual resistances. Now it's possible that we have very high Reynolds number in one phase, either the gas phase or the liquid phase. Now if you have very high Reynolds number, mass transfer coefficient will be very large. So if mass transfer coefficient is very large, then the resistance across this gas film will be very small. In other words, the drop, entire drop from the bulk phase YB or YA we had, YB and XB can be assumed to be distributed only across the liquid film, because mass transfer coefficient in the gas phase is very large. So there is no diffusional resistance here. Similarly, if we have very high Reynolds number in the liquid phase, relative to the gas phase, so we can assume that the mass transfer coefficient, or we can calculate that mass transfer coefficient in the liquid phase is very large. The diffusion resistance or the concentration drop from the bulk phase in the liquid to the interface is very small, and we can assume that entire drop, entire concentration gradient drop across the bulk liquid gas phase and the bulk liquid phase is distributed only across this liquid gas phase. Okay, so we can have two special cases which we summarize here, that we have two extreme cases or special cases. In one case, if the Reynolds number say in the Y in the gas phase is very large, all it means that mass transfer coefficients in this liquid in the gas phase is very large. That means entire drop concentration gradient which we have across the two films, we can assume everything is concentrated in the liquid phase, because mass transfer coefficient in the gas phase is very large, very high. Okay, We can also have the second case when Reynolds number in the liquid phase is very high. If that happens, then individual film mass transfer coefficient in the liquid phase will be large, and we can assume that entire concentrations is distributed in the gas phase. Okay, so one which is smaller, here kx is large, ky is smaller, so we have the entire resistance across the gas phase. Unlike here, if we have the gas phase mass transfer coefficient very large, that means the entire diffusion resistance is distributed over this liquid phase. So with that, physical understanding, if we go back to the previous expression which we obtained for overall mass transfer coefficients, we have 1 over ky over 1 over small ky plus m dash over kx. Let's assume that kx, individual kx is very large. That means the Reynolds number in the liquid phase is very large. We have the bulk phase in the liquid phase approaching to the interfacial concentration, so there is no drop here, and with that, if we take the limit kx tends to infinity, a very large ky overall mass transfer coefficients can be approximated to individual mass transfer coefficients, ky equal to ky, small ky. Similarly, the second case we can have a second case if we choose here, in which case case 2, if we say that small mass transfer coefficients in the gas film will be very large because the Reynolds number is very high. In that case, bulk phase gas concentrations will approach interfacial concentrations, and we can say that capital Kx overall mass transfer coefficient in the liquid phase is approximately equal to small mass transfer coefficient in this liquid phase. In other words, this one is the liquid film control mass transfer rate. Or we are saying here that diffusional resistance across liquid film is much larger than that across gas film. Okay, and in this case, XAB minus XA star, this will approximately equal to XAB minus XAI, right? So we can go back and even similar situations we have in this case. The first case, when we say that ky equals ky, we can say that y bulk phase concentrations minus y star is same as yb minus yi, because there is no resistance in the liquid phase. Alright, because mass transfer coefficient is very large, because Reynolds number is very large there. Okay, so essentially all these two cases, we must again go back and see the physical interpretation. See, we have interface here, and if gas phase resistance is negligible because we have high Reynolds number, so the bulk phase concentration will approach approximately same as interface. It will approach the interfacial concentration, and then all the drop will be in the liquid phase. If the liquid phase mass transfer coefficient is very large because the Reynolds number is very large, then we have XB approaching to XI, and all the drop or most of the drops will appear across this gas film. Okay, so these are the two extreme cases. In reality, if both the film resistances are high, then one has to take into account both the diffusion resistance. Okay, so in other words, graphically, if we have this interface, then in one case this is your gas film, this is your liquid film, we have the situation like this, and then it drops. So all the resistances across this gas phase here, it almost reaches, is negligible, and then we have this drop here like this liquid phase. In other case, we have all the resistances in the gas phase, then the drop will be across this gas film, and here there will not be any resistance or concentration drop here in this liquid phase. So these are two special cases, we should keep it in mind. Okay, so now what we have done, let's sum up. We have equilibrium given by the thermodynamics. So given mole fraction in X, we have Y. given partial pressure in liquid phase, we have gas phase concentration in the other phase. So this is thermodynamic, and now we can mark our operating points. We can all the 4 concentrations with the bulk phase, in the gas phase, what is the driving force, Ya minus Yi or Ya minus Y star, etc. So these points now we can mark based on our discussions which we had in the previous lectures. Now we will like to draw the operating lines. Operating line is nothing but given bulk phase concentrations, what is the liquid phase concentration, and this has to come from this material balance. Or given the liquid phase concentration anywhere in the interface or within the column, how much is the gas phase concentrations. So we have equilibrium, and now we will have the operating lines. Okay, so let's try this, derive this material balance in the absorption column, for example. Okay, so we're starting with material balance, and we assume steady state. Now we have 2 cases. One is continuous contact process, and the second is stage wise. So this we discussed in the previous lectures, that we have 2 types of contactors. One is continuous backplate, for example in case of absorptions, or we can have stage wise contactors or cascades in case of distillations. So now we are trying to make a material balance in these 2 cases. So first we start with this continuous contact process. Okay, so let's say that we have this column, backplate column, in which we bring this stream, we call it E, symbol E, we bring in contact with another stream, we give a symbol of R. We can assume that, for example, this is your liquid phase and this is the gas phase. So gas phase is brought in contact with this liquid phase, and so this contact is co-current because they are in the same directions. And we have this treated stream which is E, and we have the exit stream here is R. So let's say that the flow rate here is E. So this end is, we mark it as 1, this end is marked as 2. So we have co-current flow. Here the flow rate, say molar flow rate is E1, and the mass mole fractions of species, let's take binary species of A and B. Okay, so mole fraction of A which diffuses in the 2 phases is Y1. So we have E1 and Y1 is brought in contact with another stream R, which has a flow rate of say R1, and it has mole fractions of A given as X1, So E1 mole per second or kg per second, or we have Y1 mole fractions or weight fractions, and we have R1 mole per second or kg per second, and we have subsequently mole fraction or mass fractions in this refinite phase. So they are brought in contact. Let's assume that only A diffuses from R to B. Okay, so throughout this contact, A diffuses from B, from one stream R to this stream E, and B is non-diffusing components. So at the exit, again we have E2 mole per second at the exit, and we have Y2 mole fractions here. 2 symbolizes this exit end, and we have R2, and we have X2 mole fractions. So mole fractions of X, this stream here will keep on changing along this. So if we choose any interface here, suppose we have X, X1 will be greater than X, and X will be greater than X2, because A diffuses from here to here. And similarly, if we have Y here, mole fractions in this E phase, then we have Y2 greater than Y, and Y will be greater than this Y1. Alright. So as R moves along the column, both mole fractions of X and Y changes. Okay, this stream gets enriched with A, this stream gets depleted with A. Okay. Now let's also define one more quantity. If you recall, from stoichiometry, we have solute free basis. We will see what is the advantage of working on the solute free basis mole fractions. So if we define X as X over 1 minus X, so all it means is the mole fractions of A free basis. So this is your A over B. Similarly, we can say capital Y as a small y over 1 minus y. So this is your A over B in raffinate phase, in E phase, and this is your R phase. Okay, so we are defining capital X and capital Y. We'll see what is advantage. Now let's make material balance. So we have a steady state and we are making material balance or species balance on A, specifically on A. Let's begin with this. So we have two streams which enter here. So we can write E1 Y1 plus R1 X1. So this stream brings R1 X1, this stream brings E1 Y1. This will equal to the two exit streams. We have E2 Y2 and we can write R2 X2. Okay, so in equal to out. We can rearrange here R1 X1 minus R2 X2, and this will equal to E2 Y2 minus E1 Y1. Okay, now look at this term here, R1 and R2, E2 and E1, these are the moles per second at the two ends, right? They will change because A diffuses into B, so this molar flow rate of A or molar flow rate of these two streams will vary along this. However, if we have defined the quantities like capital X and capital Y equivalent to this, we can also define a quantity as Rs. So what is Rs here? This is also a moles per second of the stream on solute free basis, which means we can write Rs, and we can define Rs such that we have R1 X1 equal to Rs capital X1, which is nothing but Rs X1 over 1 minus X1. So all we have done, we are substituting, we want to substitute R1 in terms of Rs. So R1 is the total molar flow rates. So this would be moles per second of both A plus B. On the other hand, if you look at this term, this Rs is the molar flow rates of B only. So it's A free basis, and you will see what is the advantage of this. Okay, so if we define this quantity, one should understand that Rs or Es will remain the same because it's only A which diffuses. So B does not diffuse in this directions, or B does not diffuse across the interface. So the amount of moles per second or kg per second of B will remain same here and here. So all we have Rs and Es, which will be conserved in both the phases, right? If you work on a R, actual R and E based on mole fraction small x and small y, then these two moles per second molar flow rate will change along the length. Okay, so it's advisable, we'll see the advantage in a minute, to work on solute free basis. That's a stoichiometry, if you recall, at some level in the first or second year of your chemical department stream. Okay, so if you substitute Rs, R1 or R2 in terms of Rs, or E1, E2 in terms of Es, just one Es, note there is no suffix here because Rs Es is constant all along the length of this contact. Okay, so we can rearrange the same equations in terms of R capital X1 and capital X2 equals Es Y2 minus Y1. So we have substituted small x1, x2, small y2, y1 in terms of their counterparts capital X and capital Y. And if it's the locations, some intermediate locations between 1 and 2 where the mole fraction is X and Y, then we can write Rs X1 minus X equals Es Y minus Y1. So essentially we have made a species balance over this envelope where we have two streams which enter concurrently and they exit here X and Y. So we can write now Y as minus Rs over Es X plus we have Rs X1 plus Es Y1. So let's box these equations, and this becomes our, as you notice from here, this is the operating line. Operating line. compare this to equilibrium line, equilibrium curve which we have. Y in terms of y star in terms of your x. So we have two lines here. One is the operating curves, one is this equilibrium curve. And notice this operating curve, y in terms of x is a linear, because rs over ex does not change. So we have a constant slope. You can call it mx, y equal to mx plus intercept constant. So now we can go back and we can draw equilibrium curve and we can draw the operating curve. Okay, and again we want to re-emphasize here that one can still work on a small y, small x, actual mole fractions of a in a plus b, instead of working on solid free basis mole fractions. And one can also work on E1, R, R1 instead of RS and ES, which remain constant along this. But since we have obtained in straight line a linear curve while using capital Y and capital X, let's work on this solid free basis nomenclatures. Okay, so we did draw our curve here. Now we have capital Y and capital X. Okay, so recall earlier we had small y and small x. So this is our equilibrium curve like this. So we can always convert y as small y over 1 minus y, and capital Y x we can write as x minus 1 minus x over 1 minus x. So we can always convert this our solubility curve or equilibrium curve given between y and x, some function of x, as capital Y as some other different function gx, etc. So we have, say, equilibrium curve like this, y as x. Now we know how to mark the points. So we have this continuous contactor. Two streams concurrently they come in and they make an exit here. We have general section here between 1 and 2. This is our x and y. So let's mark this point 1 as P. So this point is P. This P has a coordinate x. This would be x1, and this has, there is a bulk phase concentration which is y1. So this is your y1. So capital Y1, capital X1 is marked as P here. Okay. Now we have obtained the operating curve, and you look at the operating curve which we had, it was linear. So if we take the slope of minus Rs over Es, minus Rs over Es, we have this operating curve. So what does the operating curve tells us? This gives us a relation between y and x anywhere between the location 1 and 2. So concentration of y, this stream, both the stream, they will change along this direction from 1 to 2. So we have P going all the way till Q at the end. So here also we have two coordinates. This would be, now this is your x1, you said. So this is now x2. Okay. And now we have this is, to start with, this was y1, and now we have this concentration, this mole fraction given as capital Y. So we have this equilibrium curve and we have this operating curve. Equilibrium curve, what does the equilibrium curve gives us? Suppose we choose any x here, all it tells us how much is this equilibrium concentrations, which means if we extend this line PQ, we will obtain another point here. We can give some name here, say T, where we can mark this point as equilibrium, YE in terms of XE. Alright, so we have one point here, PQ, and now we have T points here. So let's try to understand the difference between the operating curve and the equilibrium curve. So operating curve gives us a relation between capital X mole fractions in the bulk phase in terms of the bulk phase of the other phase, bulk concentration of the other phase. So if you have X, given X, we can find out Y, or given Y, we can find out X. What does the equilibrium curve gives us? This gives us the equilibrium between the two streams. So if we have P here and we want to find out what is the driving force, we have to go back and draw a slope of minus Kx over minus Ky. So this operating line must not be mixed up with equilibrium line, with this driving force line, which is minus Kx over minus Ky. Similarly, we can draw another line here. So we have an operating curve. Let's redraw here, which is PQ, and we are drawing another line of a slope minus kx over ky, and wherever this intersects right here, this will give you interfacial concentrations yi, and corresponding to this we will get xi. So it's very important that we mark all these points: bulk phase concentration, interfacial concentrations. So these two phases we can mark to obtain what is the driving force for mass transfer yi minus y here. So with these two curves, operating curves, which is the linear here, and the equilibrium curve yx, now we have all mole fractions of y and x between these points p and q and this equilibrium curve. Okay, physically all it means that we are trying to say that we have an interface of the two phases. We have this co-current, two phases, the gas and the liquid gets in here. We have the bulk phase, it drops to some interfacial concentrations. Then we have this bulk phase in the liquid phase concentrations. So we have y, we have x, we have yi, we have xi. Equivalent to this y, we can have x star. Equivalent to this x, we can have y star, and these points can also be marked here. If I take this point P here and go vertically upward till it reaches the equilibrium curve, that will give us y star. So if we take this x1 here and go to this vertically, we will get y star. Similarly, in some locations from 1 to 2, we have the same situations. There will be interface concentrations, then there is a drop in the liquid phase, then we have this bulk phase concentrations. Okay, we like to redraw this here in different form. So now we have two phases, gas and liquid, flowing counter currently, and we are saying that from the liquid phase x, there is this E phase here, we had E phase here, there is a diffusion of A into the other side of the interface, which is the gas phase. We can also have different situations where from the gas phase A diffuses into this liquid. So we have, say, let's assume that we have the same systems: sulfur dioxide, air and water. So we have mass transfer of sulfur dioxide from air phase to the liquid phase. We can have a different situation where the liquid is already saturated with sulfur dioxide, and then we bring this in contact with the gas phase. In that case, there will be mass transfer from the liquid phase to the pure A. Okay. So what we drew earlier, we had the equilibrium curve, and there was a mass transfer from the X phase, liquid phase, to this gas phase. Let's draw the similar situations, co-current. So two streams get in one end, from one end, and they exit from the other end, and now we have a transfer from the top to the bottom. So let's draw this line, draw this equilibrium curve here. So equilibrium curve will be the same, y versus x, excuse me. We have this equilibrium curve. Now we are discussing, we have this continuous contactor in which the two streams make an entry here, E and R. But now we are saying that there is a mass transfer from E phase to this R phase. So one can again make this material balance between 1 and 2, or between any locations between 1 and 2, x and y, to obtain, we have a similar linear equation, except now this point 1, if we call it P, is marked here as P, and we will get a straight line, linear line, which will go from P to Q as an operating curve. So there is no difference between the two, except that now we have this operating line on top of this equilibrium curve. So here we are discussing the mass transfer from E phase to R phase. Unlike the previous case where we had this PQ, we had the mass transfer from this R phase to this E phase. Here also we can extend this line to hit this equilibrium, which is the maximum mass transfer you can have. If you want to draw the different driving force, then one can draw another line with the slope of minus kx over ky to obtain yi and xi for the P. So we will have yi and xi. Similarly, here also we can draw this line to obtain this two phase interfacial concentrations. All right. So the idea is that we have one equilibrium curve, and we can have we have the operating curves like this, depending upon whether we have mass transfer from R phase, E phase to R, or we have R phase to E phase, P, Q, and we have P and Q. We can draw this slopes of constant minus kx over ky. Here this is slope of minus rs over ry, flow rates of the two streams, and we have minus kx over ky, and this is the flow rate of, we have r over s, excuse me. So this is your r. So we have the slope of minus rs over es, and we have the slope of minus kxy for this. For qp also we have minus rs over es. So all these points, all this one line in here, one is the equilibrium curve, and two lines here with the slope of minus kx and ky will give us driving force for mass transfer, either here or here. So we can identify these points, and then we can do further calculations equivalent to this. We also have an interface, and in which we have drawn the different drops or different concentration gradients. Okay. Now, similar to this continuous co-current continuous contactor, we can also have counter current flow, in which case one stream enters in from one end, and the other streams E phase enters from the other end. So both cases we have in the industrial applications. We have co-current and counter current. What is the advantage of counter current over co-current, etc.? We will see in a minute. But more important is to draw the equilibrium curve and the operating curves. In the case of co-current, we have obtained a straight line between P and Q, the two ends, as slope of two flow rates, Rs over Es. So let's see what equation which we get here in case of counter current. Okay. So we have counter current contactor, so counter current contactor, and now let's assume that this phase E, so we have E1 here and the mole fraction Y1, so 1 and 2, and now we bring the R phase in the opposite direction from the other end. So we have R2 and X2. So 2 means the second end. So this stream enters here and leaves here. So this becomes now R1 and X1. And we have this stream which is now as E2 and Y2. So we have essentially two phases here, and we can assume again we have binary mixtures of A and B, and only A diffuses, say, from R phase to E phase. Okay. Now as X2, as this stream enters from this directions to this here, this mole fraction will be larger. If you take any intermediate sections where the concentration mole fraction here is small x and here it is y, then we have X2 greater than x and greater than x1, and here y2 will become greater than y2 will become greater than y greater than y1, as we have enrichment of this stream with A. So y2 will be greater than y greater than y1, like this. Here we have x2 greater than x1, excuse me. So now if there is a mole transfer here, sorry, I think this is not correct. Let's correct this. So we have mass transfer of A from X, from this R phase to E1. So X2, so this would be X1 greater than X, and this is greater than X2. So we have mass transfer from here to here. Okay. Now we can also make material balance the way we did it earlier. We can write similar to this E1 and R1. We can define RS and ES. We can also define capital Y and capital X.
Good.
So if we work on this solid free base quantities, so we have capital X1, capital Y1, we have capital X2 and capital Y2. Since ES will be constant here. We have ES, we have RS here. Okay, we can make the material balance the way we did earlier to obtain ES as Y1, capital Y1 minus Y. So we have capital X here, capital Y here, equal to RS X1 minus X, and now we have the operating curve as Y RS over ES X plus ES Y1 minus RS X1 over ES. We can box this line, this equation. Notice the difference. We have now positive slope. Okay, which means if we now draw the operating curve for counter current system, starting from P and Q, the two ends 1 and 2, now we will get this operating curve which would be positive. So this is different from what we had in case of co-current, where we had the equilibrium curve which will be the same as before, and we had the operating curve which has a negative slope minus RS over ES. Okay, so in other words, if we draw it here, capital Y, capital X, we have the same equilibrium curve. Now if this is point P equivalent to Y1 and X1, then we have the slope of the curve which is positive, and we have PQ. So this is a positive slope here with the slope RS over ES. Here also we should be able to mark all the points here. Operating curves at any location between this, given X, we have given Y, right? We can also draw, if we want to find out the driving force for mass transfer, then we can draw this line with the slope of minus kx over ky, with the slope of minus kx over ky at any location between P and Q to obtain these interfacial concentrations at yi, xi, etc. Okay. More important here to note here is that, unlike in the previous case where we had a negative slope curve between P and Q, and if we extended to obtain equilibrium as some marked location T, here we don't have that exact situation, except that whenever, depending upon the type of this equilibrium curve, where this line, if it extends and touches this line, we will have zero driving force at that location. So this point T will be equivalent to this T what we obtain in case of this co-current flow. Okay. And the second important point to note here is that if we find all the driving force between P and Q at any location, we draw this minus kx minus ky and find this driving force for mass transfer as y minus y star, or x minus x star, or y minus yi based on the interfacial concentrations or individual mass transfer coefficients, or x minus xi, etc. It's easy to show that the driving force for mass transfer here in case of counter current is much larger. In general, this will be greater than what we have in case of co-current. Okay. So very important conclusions we have. Of course, we marked all the points here. PQ is driving force, operating curve, PQ, the driving force minus kx minus ky in equilibrium curve. More important to note here is that driving force for mass transfer in case of counter current is in general is greater than driving force for co-current, and this has a huge significance implications. The height of the column in this case will be smaller than the height of the column in the co-current, or the size of the equipment or the co-current will be smaller than the size of this co-current. Let's sum up what we have done so far. We have the equilibrium curve which is given by the thermodynamics, then we make material balance to obtain the operating curve. So if it's a co-current, we have negative slope. If we have counter current, we have the positive slopes, and the operating curves could be below the equilibrium curve or it could be above the equilibrium curve, depending upon we have the mass transfer R phase to E phase or E phase to R phase. Okay, so we should be able to draw the operating curves and equilibrium curves for all scenarios, whether we have diffusion from A, from one stream to this stream, R to E or E to R, co-current to counter current, and we should also be able to draw the driving force for mass transfer in terms of y, yi, or y, y star, or x, xi, or xx star. All right. So these are the four important curves which we have learned in this course or in this lecture how to draw it. Let's quickly draw those curves qualitatively again. So we can draw like this: yx1, then we have yx semi-curve curve like this. So this is 1, this is 2. So these are the two co-currents, contactors. You can also have yx like this, and we can have yx with the semi-curve curve and the operating curve given like this. So you should be able to make out that in this case and in this case we have co-current, but the mass transfer is from x to y phase, while in this case this is from your y to x phase. Okay, so similarly we have this situations and this situation. We have drawn operating curve, equilibrium curve. We've drawn equilibrium curves here, operating curves, and we should also be able to mark all the slopes with minus kx minus ky to obtain the interfacial concentrations at any locations between interfacial in the contactors, the co-current or the counter current. In general, as we said here, that driving force here, you can see that the difference between this and this is much larger. Average driving force from P Q is much larger here than in case of this co-current, which means if the driving force is large here, the size of the equipment will be much smaller in case of counter current than in case of this co-current. Okay. Now, before we take up the next lecture, states. So we said that so far we had two cases. One was co-current and counter current for both for continuous contactors. So these are like absorption columns. Okay. Similarly, we can have stages, cascades, just like in a distillation columns. So there also we have the same equilibrium curves or similar equilibrium curves given by thermodynamics, and one has to make a material balance from stages, between the stages, one stage, second stage, third stage. These are not discrete, unlike the previous case we have seen, it was a continuous. So if you have a discrete, here also we can make a material balance, we can draw the operating curves, and we can mark all the salient points on the curve in terms of interfacial concentrations or the bulk phase concentrations or equivalent y star or x star we discussed earlier. Okay, so with that, that would be the introduction to this diffusion mass transfer. Before we will take up some few examples, and then we will switch or will take up one unit operations, say unit absorptions or distillation or extraction.